Okay, can y'all hear us now? Yes, okay.
Extension cord over there, because that's up into the computer.
They can hear you now. No, they can't.
Yes, they can.
But they did. They have no hope.
Can y'all hear them? Yeah.
Okay, so, hang on a minute. Y'all bear with me, I'm playing with my new toys.
What am I hoping to get for Christmas?
Yeah.
Yeah, I'm gonna get a lot of clothes because I want.
Mr. Locker said that me and Mr. Steckbeck are the only ones using our swivel or trying to use it like it's supposed to be.
I like this one. It's very helpful.
As soon as I get my adapter in, I'll have it hooked up.
So weird.
So this.
I want the Pride and Prejudice.
Oh, yeah.
I
You can buy that yourself for
I've already
like
done
$5.
it. There's like, yeah.
No,
I want like a really
she
good
wants,
one.
yeah.
I've already
Like
like
a
done their
pretty
tree,
one.
and I'm pretty sure one of them's a book. I know one of them's a book.
Oh,
I already have some really- I was picturing.
I do that all the time.
Or like, I don't know if there's like any opening, so I can like see.
Or like a
But they
bag,
get it
I'll
really
be
good.
like looking over a bag.
Guys, you don't like to be
No,
surprised?
no, I like.
I
looking
do,
at
but like
pictures.
I'm constantly I'm like, what is it involved?
No, okay, this year, y'all can't look.
I know, I'm so bad. But I don't like
That's too
actually
late.
open.
No, okay,
I've gotten shoes, I've gotten a book.
Oh my
Like,
god,
here,
yeah. You look like
No, I just like shoot the same.
You stay up for like 3 in the morning on Christmas.
Yeah.
That's when you stock out and like start shaking stuff. My
Okay,
brother,
almost there.
my cousins, like, they will unwrap it and then wrap it again.
We can't hear you.
We can't hear you.
We can't hear you, Mrs. Belcher.
Hello? Can y'all hear us?
Oh, she can hear that.
We can't hear you though.
Yeah, we can't hear you. We can read though.
Just not lips.
Exactly.
Keep talking?
Okay. What's up, Lois? How you doing?
Why? We still can't, this is useless.
Oh, it's the speakers.
It is the speakers.
That's too bad. Hi, Sierra.
They can hear us, but we can't hear them, I
Is
think.
Sierra the tech master?
Sierra, I didn't know you were such an IT.
You Shawn Michael now? You're the new Shawn Michael.
Michael.
No.
No, never mind. You're not Sean. You can never be Sean. Louis, they could be making fun of us and we would never know.
Very true.
Louis, we should just pretend we don't hear him so we don't have to do anything.
You just heard that, Brian.
That'd be funny though.
Stupid. This is so weird. No.
I'm not lying.
I'm offended that you would even suggest that.
That would be pretty diabolical of us. Wait,
You're not lying.
Cameron.
No, we really can't hear you.
Wait, hi Maddie, can she hear me? No, she can't hear me.
I guess not. Just wait till she puts this on YouTube and then she'll believe us.
Oh, this is recording, right?
Yeah.
Yeah.
That's funny.
We need subtitles.
I want to read.
Untrue.
So Cam, how you doing?
Good. Oh my gosh, guys, I didn't even tell you I've been having COVID symptoms.
Have you actually?
Yeah.
What is it? Are you coughing?
Huh?
Or like
No, just like no taste
Oh really?
and
Oh.
no smell, yeah. And like everything's been smelling weird. Like when you're sick,
Yeah.
you smell, yeah.
Yeah, I
Have
have
you
like
gotten your results back?
some congestion.
No, not yet.
Oh no.
I just got tested yesterday. I get them back in like 4 days.
Oh shit, that's a long time.
Yeah.
Yeah,
Just gonna
3
stay
to 4 days.
You're just gonna stay at home.
Yeah, until I get my results back.
Yeah.
But even if I did catch it, like it's already been like 2 weeks.
Really?
You know what I mean?
For like the symptoms? Like
Yeah, no. It's been like a week with the symptoms, but
oh, okay.
like if I did get it, like we probably all got it from Camp Eagle.
We probably did.
What if Camp Eagle gave it to us and not the other way around?
Oh shoot, that's right.
I wonder if they got it.
What if it's their
I don't know who it was that we got it from. Because I know Ian tested positive first. Did I get it from Ian?
I mean, yeah, I don't
It's
know.
possible. But then we were like in the same cabin. So how did you not get it?
I don't know. Like I literally feel just fine.
That's
Did you
Oh.
test? Did you get tested or no, Lewis?
No. But I doubt I have it. So
Yeah.
that's why I'll probably be back to school on Thursday.
it's funny. That's,
Only 40 more minutes.
Already actually.
oh, it's Ian's birthday today, actually. Wearing a Y pack. Yo, Lewis, I'm wearing the I Gave Blood shirt.
I don't even know where mine is.
Dude, it's too big.
I made a little poster for mine. I made like a Canva poster for people to give blood in my name.
really?
Yeah. So I'm sending it to
I
like
think
literally.
Mr. Belcher did when we did it in the blood drive. Because he asked if there's anyone who needed to donate blood in their name, and I said Cameron. So he probably got one donation already.
Wait, when can we donate again, Brian? Is it like 6 weeks after or 8 weeks?
Probably, I think it's, wait, I have the paper in front of me, actually.
Maddie, hello.
Maddie, hi, Maddie, how you doing? 8 weeks. 8 weeks. Where's Sean Michael when you need him?
He's at Flower Bluff. Or maybe at home doing nothing.
Have you seen the kid?
Been like 2 months.
No.
Poor guy.
Poor guy. No, we can't hear you. We can't read lips. So that doesn't help.
I hear Sam.
No. Oh.
Oh!
Yeah.
Oh, it works.
Wow.
Wait a minute.
How'd you do that?
Supposed to plug that in there.
Maybe.
Oh, maybe.
Cool.
But it should be
Genius.
so they weren't like.
No, we weren't lying, Kate. Gosh.
Hey, I don't know. It was
You
you
were
that
kind of
said it.
responding at certain times that seemed a little suspicious.
Yeah.
Yeah.
You were
And Louis,
responding?
you laughed at one point.
You did.
It's true, right when they said something funny, so it
So
was
when I
like.
plugged that in there,
No, we were talking to ourselves, actually.
Yeah.
I called Louis.
Me and Brian were talking like the whole time. So
Yeah, I called him.
You're right.
okay, well.
Uh,
talk about rude.
now we're gonna pretend that we don't actually hear you. Come on, Liz. Join me.
No, that's not gonna work.
Were you saying something?
I did.
Liz,
Am I running over? Okay, I'm turning this around. Okay. That's okay. Now I forgot why I was turning this around.
You can see us.
Okay. well, I can see.
You can see that's what. It's illuminating. There you go. Ava, you're not in
Are y'all all in there?
Scoot a little more that way. So Ava can see.
Where's
There's
everybody?
Ava.
Let's see,
Now
is she-
Kyla's not.
That's okay, guys. I don't have.
You just get Ava to sit by Kyla or something.
Yeah.
Okay.
Now this is weird.
Already has a chair.
all right, Sarah, you just made it weird.
They can see.
That'll be the perfect one.
Okay, can you hear me? Yes,
Like
okay.
they're like no.
Oh, well. When I plugged those speakers in earlier in the same place and I played music over my laptop, I could hear the music coming out of the speakers. So why couldn't I hear y'all coming out of this? Wait. Did we hear them coming out of the speakers?
Yeah, we heard them, but they
they
couldn't
couldn't
hear
hear
us.
Which the people on the radio or the music? Okay, well, so that's weird. Anyway, so open your books. We're gonna continue reading. And we're actually gonna get some math going here too. A little bit. And get out your formula sheets because we're gonna run across some formulas that you want to write down. Oh, that was fun. And was it y'all who were, I was asking about Descartes, no? Those are juniors. I said that Descartes was from Italy, but it was not in France. I was gonna correct that. I forgot. Okay, first of all, how many types of energy can y'all think of?
Kinetic.
Kinetic energy? What else? What's another kind of energy? Lewis, get your camera back on.
I'm trying to find something. I can't find my pen.
That's sad.
Turn his camera off. Or turn his phone? Where did he use
Oh,
it?
sorry. I was on Zoom. I turned my camera off because
I
my
can
dog
hear y'all.
here. I could see her outside the window. I had to go rescue her. Poor Lucy. She's
Okay, so I just curious, how many of y'all attended or video streamed the chapel yesterday? Blank look. So, I didn't think so. I was just wondering. How about small group today?
Were we supposed to like link for that?
Now we
Yeah.
don't-
Because I didn't have a link for my class. So yeah, for chapel there is one somewhere on Facebook or something. But
I don't have Facebook, so
on YouTube.
YouTube, yeah, YouTube.
I don't have YouTube either, guys. Sorry.
You really need to get it.
Mhm.
Okay, so we're on page 139. Is everybody there? 139. Everybody in here, I think everybody read. No, you didn't. Why don't you read for us, Ava? She's going to start reading for us. Y'all follow along, and then I'll be calling on y'all to read as well on you virtual people. Okay, so under section 5.2, forms of energy.
The SI unit of measure for energy is the joule, named after one of the pioneering English physicists of the 19th century, James Prescott Joule. Joule discovered the relationship between heat and mechanical work, which we will address shortly. Ultimately, his work led to the formulation of the law of conservation of energy.
Okay, stop for a second. Can y'all hear her read?
Yeah.
A little bit. And y'all are following along?
Page is this? Sorry.
What?
What page is this?
139.
Okay.
Okay, continue, Ava.
For some of the forms of energy we will study, there are simple equations for computing energy quantities based on a couple of system variables. The combinations of units of measure resulting from any of these calculations are equivalence joules. In terms of SI base units, the joule is defined as that equation. The term power refers to an energy rate and the rate at which energy, U, is produced, consumed, or transferred in a standard period of time. Or that equation.
Okay, so let me interrupt you again. So I've always, and you've probably always used an E to represent energy, right? Like in the John May's chemistry book, is E equals HB over lambda. And now, and even on page 138, he has an E for energy. But now starting on page 139, he's using a capital U. And he does that throughout the chapter, which is kind of annoying to me, but I guess we all better do the same thing so that everybody knows what everybody else is doing. Okay, so think of U, capital U as energy. Okay, anybody have a good way of remembering that? Remember. Okay, so anyway, P is U over T. In other words, if you take the energy and divide by time, that's the power. So power is in watts. They're going to talk about that here in a minute. And everything else we're going to talk about is energy. Power is the only thing we're going to be talking about that's not energy. It's the rate of energy. All right, instantaneous or average rate. So that equation you're going to want to put on your formula sheet. P equals U over T. And make sure you know that P is power and U is energy. And you're probably already pretty familiar with T being time. And if you want to write down what the units are too. So the unit for power is watt, capital W. And the unit for energy is joule, capital J. So since I already mention what a watt is, flip over to 140, and Ava, I'll let you finish reading down to the example.
The Watt is named after James Watt, a 17th century Scottish engineer whose work improving the steam engine contributed significantly to the arrival of the Industrial Revolution. The efficiency of an electrical or mechanical system is defined as the ratio of useful power output from the system to the total power consumed or taken in by the system, or this equation.
Efficiency equals useful power output over total power input. And so you think of, if you have like a machine or something, say you plug in a computer or you plug in a fan or whatever you plug in, it's getting a bunch of power into the radio or fan or whatever you're plugging in. It's getting all that energy and that power. And then it's going to do work, and then it's going to produce power. And so you have to find out, some of the energy is, and the power is going to go into just heat and friction and stuff like that, going to get wasted. And so you're always going to have a waste of energy. And so there's always going to be, you can measure the efficiency of it by dividing the output by the input, the smaller number by the bigger number, because the output is always less than the input. Does that make sense? You can't build a machine where the energy you put in, that it increases that and puts out even more energy, or even the same amount of energy, okay? There's always the amount of energy that comes out is less than the energy you put in. Okay, and so then they have an example there for an ordinary electrical light bulb or lamp designed for helping humans to see. I'm not sure why he said that. The useful power produced is the electromagnetic energy emitted by the light bulb in the visible spectrum. The power input is the electrical energy delivered by the electrical system to the light bulb, indicated by the power rating of the lamp. Typical efficiencies for common types of lamps are as follows. So incandescent light, 2% efficiency. You know, those kind of light bulbs, those are your normal light bulbs that look like, you know, your bulb with a little filament inside of it. They're not used as much nowadays. And have you ever touched one of those and it's been on a while? They're pretty hot. So a lot of the energy is going to heat, getting wasted. Only 2% of the energy is turned into light. That's what they mean by the efficiency there, 2%. But then if you get those compact fluorescent light bulbs, the efficiency's only gone up to 7 to 9%, which still most of the electricity is being wasted. And then they have LED lamps or lights from 4 to 18% efficient. Okay, and so here's a question they have. For a 10-watt LED lamp operating at maximum efficiency, determine the useful power output and the total electrical energy consumed by the lamp during 8 hours of operation. Okay, so that's the kind of problems you're going to be seeing. So let's think about what they gave us there. What is the 10.0 watt? What is that? What's the symbol for that? Or what is that a unit of? Watt is the unit for power. Watt is the unit for power. Okay, so they just gave us power. So you put P equals 10 W. Power equals 10 watts. And then it says it's operating at maximum efficiency. And so we look up there at LED, the maximum efficiency would be what? 18%, which you would change to 0.18, okay? And then to determine the useful power output and the total electrical energy, first of all, I could write this on, I'm going to share the screen and write it down, and then y'all can see it. Y'all are going to be doing some of these also. So how can I, there it is. Ooh, I'm going to get rid of those guys. Okay, so we said power equals 10 watts. Efficiency, they don't have a symbol for that. You just have to put efficiency. And it's 18%, that's the maximum, or 0.18. And then, everybody see that on the screen? Not too bad. we have an equation. Let's put that over here that they gave us earlier. Efficiency is equal to, they say useful power output. I'm just going to put power output. Over total power input. I'm just going to put power input. Okay, here's what how you should write it. And then they have a little times 100 over here. And they say 100%, but it should be just times 100, and then that gives you the percentage. On your formula sheet, you should write efficiency equals PO over PI times 100. That looks like a U, so let me change that. Okay, does that make sense? P over PI. Okay, and what are they asking us for? It says determine the useful power output. Okay, so this is what we're looking for. And the power output, I think they're using that equation from the previous page. Put it over here. Actually, we have that. They don't do that. Okay, so we have 18 or 0.18 equals PO over PI. And the 10 watt, okay, so that is the input. I'll put that over here. P input is 10.0 watt. Okay, so and so your power output would be 0.18 times 10.0 watts, which is 1.8. And what's the unit for power? Watts. It's kind of a joke. And I usually use little W's, but he uses big W's. So we'll do big W for watts. Did that make sense? Some of these, it's just knowing what in the problem is what you're using it for. That's a tricky thing to figure out. Okay, and then the energy. You can use this equation. The energy is going to be the power times the time. And you want everything in MKS, right? And so they say 8 hours. The time is 8 hours. Well, we need to convert that to seconds. And he does it there. He gets 28,800 seconds. Y'all know how to convert. 28,800. Okay, another zero there. And so your energy would be, he uses the 10 watts, not the output, they use the input. So this P right here would be power input. Okay, so 10 watts. This is hard to write. And then the 28,800 seconds. And you end up with joules of 290,000 joules, which we write as kilojoules, just 290 kilojoules. Okay, so that kind of thing makes sense. Just being able to label what things are is a tricky part. Okay, forms of energy. So I'm going to stop sharing. Actually, I'm going to clear. This is so much easier to erase than the board. Where's my, I can't see my cursor. There it is. And we're going to get Brian to read for us. Starting below the example on 5.2.2 forms of energy.
There are many different terms used to describe the forms of energy present in various physical and chemical systems. We will continue our study of energy by reviewing these, working a few example problems.
Wait, we can't hear you. You muted yourself. There we go.
Note that there is no generally accepted convention pertaining to the symbol used to represent energy as a variable in equations. You will find a different symbol in nearly every text, and some texts use more than one symbol. A convention that is in fairly wide use in physics at the college level is the symbol U, but the subscripts used with this symbol to represent different forms of energy still vary. In the discussion below, I will use the symbol U with a logical subscript.
Okay, keep going.
Gravitational potential energy. This is the energy an object possesses because it has been lifted up in a gravitational field. If such an object is released and allowed to fall, the gravitational potential energy will convert into kinetic energy as the object accelerates. The term potential in the name of this form of energy indicates that the energy is stored and has the capability of converting into another form of energy, such as kinetic energy or heat when released. There are other forms of energy listed below that use this term for the same reason. The gravitational potential energy possessed by an object is calculated as UG equals mgh, where m is the mass of the object and h is the height above a given reference. Note that since the weight of the object is equal to mg, the equation for UG is equivalent to the product of an object's weight and height. Note also that gravitational potential energy is a relative quantity. There is no absolute reference for height, so there is no meaning to the term gravitational potential energy in an absolute sense. The gravitational potential energy we calculate for a given object will be relative to the reference used for measuring the object's height.
Okay, I'll interrupt you then. So they have U sub G for the gravitational potential energy. And you think, well, maybe they should put P for potential energy. But this is specifically for gravitational potential energy, as opposed to what we're going to see later as spring. I think it's elastic potential energy that you have in springs. And so in that case, he puts U with a E below it. Yeah, on page 144. So be sure you need to put that down on your formula sheet too. Okay, UG equals mgh. In the past, we've always just put PE for potential energy, PE equals mgh, but we're going to use UG. And the next one is kinetic energy, and we usually have written that as KE, but he uses U sub K. Okay, so we'll get Lewis to read that one.
This is the energy an object possesses because it is in motion. As I mentioned in the previous chapter, there are multiple ways an object can be in motion, such as translation and rotation. Here we will consider only translational kinetic energy, saving rotational kinetic energy for a later chapter. The faster an object is moving, the more kinetic energy the object has. The translational kinetic energy, UK, of an object is calculated as UK equals 1/2 mv squared, where m and v are the mass and velocity of the object.
Okay, thank you. And so he jumps into a pretty technical one. Instead of saying, here's a ball moving at 3 meters per second, what is its kinetic energy? Instead, he says, we've got this hydroelectric dam with all this water. And let's see. And it generates electricity by converting the gravitational potential energy in the lake water behind the dam to kinetic energy. As the water falls into the turbine inlet, you see where that on the picture is? The water falls into the turbine inlet. The gravitational potential energy of the water is converted to kinetic energy of the water. And the kinetic energy spins the blades of the turbine. The turbine in turn spins the windings in an electric generator, producing electricity or electrical power. Okay, so then he has the problem, this is on page 142, assume that a certain hydroelectric dam There's 750,000 cubic meters of water per hour, and it falls an average of 43 meters to pass through the turbine. Determine A, the electrical power output of the system in megawatts, assuming the turbine generator system operates with 55% efficiency, and the average velocity of an average cubic meter of water when it arrives at the turbine system, assuming 100% efficiency. Okay, and so it takes us through, if you notice there, we're given a volume of water. We have to look up the density. He said that's in Appendix A. He gives it there. And you have to use a density equation to find out the mass of the water. So you have to be aware of that. Sometimes they won't give you the numbers you need for your equations. You have to find some other way to get it. And then he finds the the potential energy by just multiplying all that mass by 9.8 and then 43 meters. That's how high it is. Okay, so the mass of the water times the height times 9.8, and you get 3.15 times 10 to the 11 joules. That's a lot of energy. Okay, and then because it has 55% efficiency and 1 hour is 3,600 seconds, they figure out the power output. And look down at the bottom, right before the end of the page. See where they say H equals 43 meters? And then in order to get the velocity of the water, because I think that's what they asked, right? Velocity of the water, they set the potential energy equal to the kinetic energy. All the potential energy is converted into kinetic energy. And so mgh equals 1/2 mv squared, and the ends cancel out. So it doesn't even matter how much water there was, or even if it was water. Anything that you drop from 43 meters up, when it gets down to the bottom, it's going to have a velocity of 29 meters per second. But see what they did there? They got velocity is square root of 2gh. As long as you know what g is, 9.8, and h is the height, then you can find out the velocity. If all that kinetic energy potential energy is converted into kinetic energy. Okay, any questions on any of that? Okay, we'll continue tomorrow with mechanical energy and elastic potential energy and radiant energy, and several more on 146 and 147. So we're just starting to get through those. Any questions there, you guys? We will be starting to do exercises 1 through 6 tomorrow. I'm sorry, 6 through 25, but we're not going to start it yet. That's going to be the next assignment. Okay. We're about done. So if y'all don't have any questions, you can punch out. They can't read yet. You have a question?
Oh, no.
They can wave goodbye to you. And next time I want to see you in uniform. Or at least move your camera up so we can't tell the.
Oh, wow.
It's hung up on me, right? Okay.
Oh.
There they went.
Wow. That kind of hurt.